Well, hi there. We're going to have a very intriguing look today at the binomial theorem for binomial expansion. Here it comes, binomial expansion, and there is a typical binomial expression raised to the power of n. Binomial meaning two numbers, in this case x and a. So x and a today, and there is lots and lots of Greek capital sigmas, which is the symbol used for the general case of binomial expansion. So, without any further ado, let's go. What have we got? X plus a to the n. Now, I'm just explaining there that binomial means two, and that's the bi, and the nomial means numbers. So it's two numbers, expansion of two numbers, yeah? Very excellent. So now let's have a look at a couple of examples. We know that x plus a all squared, that's a binomial expansion where we're raising the linear expression x plus a to the power 2. And then you get x squared plus 2ax plus a squared, don't you? Now if we have a look at x plus a all cubed, we've got x cubed plus 3 times x squared a plus 3 times x times a squared plus a cubed. Yes. Now, let's have a look at Pascal's triangle, because Pascal's triangle is extremely significant in finding the coefficients of the expansion terms in these polynomial expansions, okay? Now, Pascal's triangle is constructed by putting a 1, it's actually a pyramid. You start at the top of the pyramid with a 1, then the next line down, you expand out and make two 1s. Now, from then on, you start on the outsides with 1s, the same as I've showed you there, but you then get all of the internal terms by adding the two terms immediately above. I'll show you. You see there's an outside 1, then you get that 2 in the middle by adding the two terms on the line immediately above either side of where that term's going to go. Okay, so there was a 1 and a 1 on the line immediately above the 2 to the left and to the right of it. So you add those two numbers to get that middle 2, and then the outside term is a 1. So let's do the next line. Okay, 1, and then you've got 1 plus 2 above is 3, and then 2 plus 1 above is 3, and then you get another 1. And so it goes. You get the deal? Have a look at it. Very easy, isn't it? Yeah, we'll do one more. Yeah, that's that line there. Okay, that's Pascal's triangle. You can keep going as long as you like with that. But what I want to show you here is that line there gives you the coefficients for the expansion of x plus a all squared. And similarly, that line there gives you the coefficients for the expansion of x plus a all cubed. And that line there gives you the coefficients for x plus a raised to the power 4, and similarly with that line raised to the power 5. Okay? Now that's pretty intriguing, isn't it? So, what can we do with this? Well, yes, you can express that. See that third line there where I've got x plus a all squared? That left-hand 1 could be written as 2c0. The combinations, okay? The combination, that's 2c0, okay, as opposed to permutation, that's combinations. And 2c0 would be 2 factorial over 2 minus 0 factorial times 0 factorial. You remember? Okay. Now, the middle term could be called 2c1. It's the same thing. 2c1 is 2. And 2c2 on the right-hand side is 1. So now look at that. These coefficients are being written as combinations, okay? Look at the next line. That one is 3c0. The next term is 3c1. The next term is 3c2, and the next term is 3c3. Go to the next line. 4c0, 4c1, 4c2, 4c3, 4c4. 5c0, 5c1, 5c2, 5c3, 5c4, 5c5, and you can see what's going on. Now, have a look at above where I had that example of x plus a all cubed before we got onto Pascal's triangle. I'm going to rewrite that expression in a most intriguing way. Have a look. Okay, now that first term could be written as 3c naught, because that's a 1, times x to the 3 times a to the naught, because a to the naught is 1, okay, which just all boils down to x cubed. Now, the next term could be written as 3c1, which is 3, times x to the 2, and you'll note that the x to the 2 is 1 less than it was in the previous term, being 3 in the previous term, and a to the 1 being 1 more than the exponent in the previous term, where a was a to the 0. Okay, now see the pattern that's going on here. Have a look at the next term. That's 3c2 now, times x to the 1, that's gone down another bit on the exponent, and the a to the 2's gone up 1 again. See, the plot thickens. Plus the final term is 3c3, x to the naught, which is 1, and so is 3c3, by the way, a cubed. Now, where we're leading with this, ladies and gentlemen, is that this gives us a generalised way of producing the binomial expansion of x plus a to the n, where n could be anything, okay? So here it comes. In general, we know that x plus a to the n, now you better have a chill pill, where the Greek capital sigma is coming with a vengeance, right? Looks very abstract, but hey, we know what we're doing because we've laid the ground rules. So it's Greek capital sigma, meaning the sum of, okay, all terms NCR now, times x to the n minus r, which actually means it phases down by 1 as you get each successive term, times a to the r, when the r is phasing up 1 with each successive term, where r goes from 0 to n. That's an interesting observation, actually. There's always one more term than the exponent for the binomial expansion. E.g., x plus a squared yields 3 terms. X plus a cubed yields 4 terms. That's why in that generalised expression there, it goes from r is 0 to n, which will get you one more term than the n exponent on the left-hand side. Did you get that? Alright, now don't freak out. Come on, this thing's reasonably friendly once you know what to do with it, okay? So put a box around it. It's a big, big, big deal. Thank you, Mr. Pascal. And Mr. Box. Sorry, Mr. Box. I should have put you first. I know. Alright, all is forgiven, I hope. Now, we've got here the r plus 1th term. This is a really important thing. This is going to get a box too, if Mr. Box hasn't gone on strike. R plus 1th term is NCR x to the n minus r times a to the r. Alright? That's it. Put a box around. Thank you, Mr. Box. Thank you. So that's that bit. Now that's really, you need to know, well, you need to particularly know that last one with the box around it. That's the one you tend to use more of. I just wanted you to understand where the one above came from. Okay, we're going to use an example as we go over the page in a minute. Now that thing there, it's restating x plus a to the n equals the sum, Greek capital sigma, from r, where r goes from 0 to r goes to n, of NCR, that's the alternative notation for NCR, times x to the n minus r times a to the r. Guys, I'm sorry I had a little bit of trouble. That's a little bit blurry and small, so I'm just having a few adjustments here to try to get the text right, okay? So please bear with me. I rewrote it for you anyway, so that it would be clearer. There it goes. Mr. Is there a box? No, Mr. Box. Oh, yes, there is. Thank you, Mr. Box. There it is, okay? Now, don't laugh, but I overcompensated in the next line. You are laughing. Therefore, the r plus 1th term of the expansion is NCR, x to the n minus r, a to the r. And then I overcompensated even more for the next line. Oh, no, about the same. So expand the expression. Expand the expression x plus a to the n equals that horrible looking mess when n is 3. That's all right. No problem. Come on, we can do that. Okay, so x plus a to the 3 equals the sum from r to 3, r from 0 to 3 of 3CR, right, 3CR times x to the 3 minus r, remember n is 3, times a to the r. Well, that's all right. Now we're just going to expand that thing, okay? And it'll lose its sting altogether. Come on, when r is 0, it'll be 3c 0 x to the 3 a to the 0. When r is 1, it'll be that thing, right? Does it look right? Yes, it does. Then when r is 2, yes, everything's looking great. It's that. When r is 3, it's that. You see how it goes from 0 up to 3, yielding one more term than the exponent 3? Yeah, so we've just got to simplify that now. Okay, 3c0 is 1, so that just gets you x cubed, because a to the 0 is 1. Plus 3c1 is 3, x to the 2, a to the 1, yes. 3c2 is also 3, x to the 1, a squared, plus 3c3 is 1, x to the 0, which is just 1, a cubed. So what have we got? X cubed plus 3x squared a plus 3xa squared plus a cubed. Yes. Thank you, Mr. Box. It's great, isn't it? So you can see what to do now. So don't be afraid of the Greek capital sigma. It just means a sum of terms, right? Find the coefficient of the x to the 8th term in that thing. Goodness, it looks beastly, doesn't it? However, we won't lose our cool. No, 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 because we're at school. Oh dear. Sorry. The r plus 1th term is, the r plus 1th term is ncr times x squared to the n minus r times x to the minus 2 to the r. Now, oh goodness, what a mess. No, 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 don't say that. It's we know that n is 20, so I think we'll put that in first. Yeah, good, good. That'll make it a little bit less horrid. That looks a bit friendlier already. Now, what do we got to do? Get the x to the 8th term, do we? All right. Let's combine all those x's and see what it looks like then. Oh, that's looking a bit better. One more line, I think. Oh, that's even better again. Now look, guys, see that x to the 40 minus 4r? That 40 minus 4r has to be what? Yeah, because we're looking for the x to the 8th term. So I can solve that now for r, can't I? Of course I can. There you go, look. Solve for r. There it is. Yep, therefore, r is 8. Ain't it great? R is 8. So, now what are we trying to do here? Oh, that's right. We know r is 8, so let's just plug it into that term. Yeah? Looks like the 7th term. Oh, no, wait a minute. R is 8. It's the 9th term, that's right. The r plus 1th term. Yeah, 9th term has r is equal to 8. And it is 20c8. That's right, because r is 8, and it's great. X to the 40 minus 32, which looks like 20c8, x to the 8. Now, that was easy as, wasn't it? The coefficient is, and I can't be bothered working it out, so Mr. Box, save me. Thank you, Mr. Box. Do you get it, guys? That's the kind of question I want you to be able to do. All right? Using that little tool of the r plus 1th term is, and so on. You can always work them out if you do that, right? So please put it on your cheat sheet at the end of the year. Yeah? All right. Now we've got to find the 5th term in the expansion of that thing. Well, that's all right. Okay, so r plus 1th term, that's our little tool thing again, in our little arsenal of tools. Right? The r plus 1th term's that thing. Now, we're going to sub, n is 7, of course, because it looks pretty beastly. That looks a bit better. Now, what do we want? The r plus 1th term. So, the 5th term. Okay. So, if r plus 1 equals 5, then what's r? Of course, it's 4. So, now we're just going to sub r is 4 into that r plus 1th term thing. I think we've done it then. We have 7c4 3x to the 7 minus 4 times minus 15 to the 4. Good. Now let's just make that a bit easier to see. Yeah, I've fixed it up a bit. Still looks pretty revolting. But look, that's the deal. That's what you do, guys. So I've just cleaned it up a bit, taken the 3 out from the 3x term, and I really couldn't be bothered working it out. So Mr. Box saved me. He's a good man. Thank you, Mr. Box. But I just want to show you what to do. You see? What to do. You do not lose your cool. You just basically just barrel in and fix it, you know, because it's easy when you've got the right tools. Okay, what do we do now? What do we got to expand this? I think that's the last one for today. 3x plus 2 to the 5. Yes, okay. Well, I've used the laborious capital sigma thing, okay? So that's 5c naught, 3x to the 5 times 2 to the naught, plus now just progressing it along according to that sigma thing, okay? I'm phasing the 3x terms down by 1 in each successive term, and I'm phasing the 2 up by 1. That's the exponents thereof, okay? As each successive term, and of course the 5c naught, and then the 5c1, and then the 5c2, and then the 5c5. Get the idea? Yeah, there's the next one. Good. There's the next one. Yes. And there's the next one. And there's one more. There you go, okay? That's it. That's the expansion. That's the expansion, okay? So you can see what to do, can't you? Yeah, yeah. I'm just making it simple for you now. Just cleaning it up a bit. There it is. There it is. There it is. And I think that's it, isn't it? Oh, one more. Okay, so that's it. Now look, I'm not going to be bothered fiddling around trying to get the end result. You can see what to do, can't you? Of course you can, etc. Aha, the wonderful Latin word which means and the rest. So, did you see the light? Yes, you did. It's mighty bright, that light. And we're right. So, let's get going and get out of here. Alright, so that was it. Binomial expansion, you can see what to do now. Now, what do you got to remember? Put those formulas in your cheat sheet and use them, alright? And don't be scared of the Greek capital sigma. He's a very friendly little beast when you get to know him. Alright, thanks again and see you later. Bye.